Okay, welcome back. This is now chapter 15. We'll start with vector fields. Okay, so we're basically going, or I believe we're going to be trying to incorporate vectors into integrals. Okay, this will give us more options for doing applications. So all right, so here we go. Section 1, just defining a vector field. And all it is a function that assigns a vector to every point in the plane or in space. Okay, so a function that assigns a vector to every point in the plane or in space. Okay, you've kind of seen this before if you took Calc 2 and you did differential equations when you were doing slope fields. If you remember the slope fields, we would put a little tick mark representing the slope of the tangent line to the solution curve at a particular point, and we would end up with this sort of, I don't know. Jeez. Sorry, I just woke up. So, and this would be slope fields. You may have to look that up. What the heck is that? I forgot. You can look it up, but it's kind of like that. The only difference between a vector field and a slope field is the slope field, all the little tick marks have the same size. Now in a vector field, obviously the vectors can be of varying lengths. Some other examples of vector fields. So examples that we know already. First off, the gradient. If you remember, the gradient is just the vector formed by the partial derivatives of the function. So you'd have like fx here and then fy here. Okay. So for any point in the plane, you could assign it this vector based off the partial derivatives, and that is a vector field. Okay. Other versions, any sort of inverse square field that you would hit in your physics class, so the gravitational field. And they give formulas for that here in our book. You've probably seen these formulas without vectors, but now they'll have vectors involved. So negative g m1 m2 for masses all over the square of the distance between the objects times this unit vector. So that would be an example if you're a physics person. Right. So let's not get too carried away with it. It's cool because now you can think of the xy plane as representing maybe wind or something like that. You can your plane will have all these little vectors. You could have it represent anything you want, really. So maybe a puddle, and you're throwing a stone into the puddle, and the puddle has sort of maybe there's a hole at the bottom of the puddle and there's water. This is getting a little bit crazy, but maybe it's a bucket, right? So it's a bucket full of water, and at the bottom of the bucket there's a hole. So it will cause kind of a for any sort of particle of water here, the water is going to be flowing towards the hole, wherever that is, and you could represent that scenario. Assuming you know enough about physics, which I don't. You can represent the scenario with vectors. Okay, so it has a lot of geometric properties that can model varying situations. You could also look at it just completely in terms of mathematics, right? You don't need to have some physical model or physics involved at all. I was just reading the other day about like Hamiltonian spaces, and Hamilton based those spaces off of like basically just logic and things like that. So there really is no geometric intuition, and I think ultimately, I think it's Hamiltonian spaces, ultimately is used for modeling quantum physics and stuff like that. But I'm already forgetting what I was reading 2 days ago. Anyways, we just want to be able to sketch these very, very quickly, obviously, and you could use a computer to do this much more rapidly, but it's not a bad idea just to sketch it, get your hands dirty, and figure out what you're dealing with. So here's a simple example. So you have, for any point, you're just gonna draw the vector y(x) for that particular point, and you can get a vector for any point you want. Generally, when I'm drawing these things, I'll just look in a certain box region like this, and you do a little t-table for the points. So x, y, and then your vector. So these guys have x-coordinate -1, and then y-coordinate -1, 0, 1. And then the vector is just taking these two components and swapping them. -1, -1. I just got to smush that in there. Sorry about that. 0, -1. Then here it's 1, -1. Okay, so we could draw those vectors in the xy plane. So -1, -1 is right here, and then the vector go to the left -1 and then down -1. So that would be a vector there, and the one at -1, 0 is 0, -1. So don't move in the x direction. Go down in the y direction like that, and then at -1, 1, we have 1, -1. So to the right by 1 and then down -1. So you'd have this vector. Okay. All right. And so on and so forth, right? So the 0 with the x component 0. And we want to be a little careful about the length of these vectors. I sort of drew it right to the other point, and that might not necessarily be true, right? The actual, well, I think that is true in this case. So the actual length is 1 plus 1, so square root 2. So yeah, that would be, I guess, square root 2 would be going from here to here. It's just the side of that triangle. Okay, so anyways, I'm not going to overthink it. So 0, -1, 0, 0, and 0, 1. So this would be -1, 0, 0, 0, and then 1, 0, right? So 0, -1 is right here, and we're putting -1, 0, so that vector would be going like that. At 0, 0, we just have 0 vector, so just put a point there. And then at 0, 1, it's 1, 0. So at 0, 1, it's 1, 0. So you go over 1, and then it's just that. And so on and so forth, right? So I could leave it to you just to get these other three vectors. But hopefully you get the idea. So you want to go through that at least once to get the idea. It's a lot like generating slope fields back in differential equations. Okay. But you can see it's kind of going to generate a picture. And then on top of this picture, you could do things like incorporate, I don't know, some sort of curve going through here. And at each point on the curve, that would be associated a vector. Okay. So you could do all kinds of cool math with this. In this new setting. Okay. Section 2, conservative vector fields. Okay, if a vector field is conservative, it gives us all kinds of nice properties that we take advantage of. And what does it mean to be conservative? That means it's kind of the result of doing a gradient operation on some unknown function. Okay, so the definition, a vector field is conservative if the vector field is equal to the gradient of some function that we don't know. Okay, this function f is called the potential function. Okay, so if you're given a potential function, in order to get a vector field out of it, you just take the gradient. So some of the questions in the homework, like 23, will ask you to do that. So here they give you a potential function 5x squared plus 3xy plus y squared, and they want you to get the vector field that's associated with it. So all you got to do is get the gradient for it, but we're going to write it as if it was a vector field. Okay, so the first component is the derivative with respect to x. So it would be 10x plus the derivative of this with respect to x is 3y. And then the derivative with respect to y is going to be, well, 3x. This will just be 0. And then plus 2y. Okay, so fairly simple, just getting a gradient. Okay, not all vector fields are conservative. So how do I know if it's conservative or not? Well, there's a test for that. And it's basically looking at the partial derivatives of the components of the vector field. Okay. So if you take the partial derivative of this with respect to y, and it's equal to the partial derivative of this with respect to x, then it's considered conservative. And you may remember from our section on partial differentiation when we looked at the mixed partials, which is basically kind of like the second derivative. The mixed partials were usually equal to each other. And you can kind of see it here, for example, doing okay, so if your vector field is this thing, the test for conservativeness is to first take the derivative with respect to x of that guy, with respect to y, and then what is that? So with respect to y, it's 3. And then take the derivative of this with respect to x. And you see that thing's also 3. If these are equal to each other, it's a conservative vector field. Okay, and how does this relate to what we did in the partial differential equations problem? Well, this thing right here is basically the partial derivative of this guy with respect to x, and then the partial derivative of that with respect to y. Okay, so it's the partial derivative of little g with respect to x, and then with respect to y. I hope I didn't get the order wrong. I forget sometimes which order it goes in. The other one, this part here, first I took the derivative with respect to y, and then took the derivative with respect to x. Okay, so it's that idea of mixed partials that we're looking at, and if the mixed partials are equal to each other, that's the criteria. Okay, I think maybe it was called the Cauchy criteria. I don't remember. Okay, but that's how you're gonna do this. If you took differential equations, you had the same process there. They teach you the same thing there, and those you're dealing with exact equations and that. So if you remember, and this looks familiar, yeah, it is. Okay, you see it in differential equations. Okay, so anyways, the test, this was just an example, and we're going to see another example here in a second. But the test, we need to make sure that given your vector field, which we usually put as m of xy comma n of xy, I'll just write m and n, we need their partial derivatives to be equal. So in particular, the partial derivative of m with respect to y needs to be equal to the partial derivative of n with respect to x. Okay? For the vector field to be conservative. Okay. Okay, I'm not going to go into the theory or the proof. You can look online on YouTube, and there's plenty of people out there trying to explain it to you at this point. So you can just go there. Right. So let's look at finding the potential function now given a vector field. So I think it's part B now in my notes, finding the potential function. Okay, so you're going to be given a vector field, so something like f of xy or xyz. You hope it's just xy because those cases are a little easier. And we'll have some function of x and y and some function of x and y here. If this is conservative, then there exists this magical potential function up here in the ether, f of xy. Okay? So we note in order to get m, what did we have to do to f of xy? So we had to take the partial derivative of that thing with respect to x. Right? In order to get n, what did we do to f of xy? Well, we took the partial derivative of that thing with respect to y. So in order to get the potential function, we could kind of reverse that process. We could say, instead of taking the derivative, let's integrate with respect to x. The only trouble is it's kind of like doing an antiderivative. You always have that plus c thing. You always have a constant of integration. Here we're going to have a function of integration, because when you take the derivative with respect to x, it's going to annihilate anything that's dependent on y. Okay? So it's not going to be enough to just do an antiderivative and you'll have your answer. No, what you're going to have to do is the antiderivative and then do the partial with respect to y and set it equal to this thing here. It's from that equation that you're going to be able to get your function. Okay? Okay, so what did I just say? Well, first, in order to get up to here, I need to do the integral of m with respect to x. Okay, and that will put me right here, but it's not going to be the perfect answer because it's going to have that constant function thing happening. So what I do then is take the partial derivative with respect to y and set that equal to n. Okay, and then I solve this thing, and it will be a differential equation at the end. But that will give me my potential function. You can also do it in the other direction. You can, all right, let's reverse the partial derivative of y. So integrate n with respect to y. That would put you here. Then do the partial with respect to x. And that would give you m. Okay? It doesn't matter which way you do it. You'll get the same answer in either way. Okay, so let's try one of these. So let's try 41. I have f of x comma y equals 2xy comma x squared. Okay, I need the potential function. First, you got to make sure it's conservative before you try this. So we do the partial with respect to y of 2xy. And of course, that's just equal to 2x. And then I do the partial with respect to x of x squared. And of course, that's just equal to 2x as well. So those are equal, so it's conservative, so we can pull this off. Okay. All right, so use either format. I'll just always go with the first one. And so what am I dealing with? The partial with respect to y of the integral of m, which in this case is 2xy, with respect to x, and that should end up equaling x squared. Okay, so do the integral of 2xy and then take its partial derivative. With respect to x, that's going to give me 2x squared all over 2 times y, which will just be x squared y. And then plus this function of y, which is annihilated by the partial differentiation of little f of x. Okay, because anything here that's a function of y would be equal to 0 when you take its derivative with respect to x. So you need to kind of add that on, just like before when you did integrals, you would go plus c. right? So plus some constant. Because you took the derivative with respect to x, anything that's dependent on y is going to be a constant now. It's just going to go to 0. So you have to kind of put that in there. Okay? And then that equals x squared. Okay. This is your answer. This thing right here is your answer. That is your f of xy. But we still need to get this g of y thing. Okay? And that's why we do this other part. We still have to take its partial and set it equal to this. Right? So I take the partial of this with respect to y. That will give me x squared plus g prime of y. And that equals x squared. And then subtract x squared from both sides. And you end up with a differential equation. Okay? So it's the derivative of g with respect to y, integrate both sides. The integral of 0 is just a constant, so you get g of y is equal to some constant. Usually they use the letter k for the constant. Okay? So in this case, it's not anything interesting. You're just plugging in a k for g of y. So my f of xy function, the potential function, is x squared y plus some constant k. And then that's your answer. That is the f of xy thing that we're after. Okay? Okay, so that's the idea. They can be a little bit more challenging when you get to higher dimensions. And if I get a chance, I'll take a look at one of those. But for now, let's move on. Okay. Speaking of higher dimensions, in order to show that something is conservative when you're dealing with 3 variables, for instance, you're not going to have the Cauchy criteria thing where you can just take the partials and set them equal, see if they're equal to each other. What you have to use is this operation called the curl. And we're also going to introduce the divergence operation as well. Okay. So it has characteristics of a cross product plus taking partial derivatives. Okay, so it's first off the curl of f of xyz, the curl of a vector field. So what is this? The way they're going to notate it is like this. So it looks like the gradient symbol crossed with the vector field. Okay, and the way you do it is let's pretend the vector field is m and p. Okay. The curl of f is going to be this kind of, you kind of use a determinant to remind yourself how it works. So ijk, and what you're doing is taking partial derivatives in the same kind of motion that you would do your determinant for 3 by 3, right? So in this case, we would have the partial derivative with respect to x, then the partial derivative with respect to y, partial derivative with respect to z of m and p. Okay? You'll get a vector out. In particular, if the curl of this thing equals the 0 vector, then it's conservative. Okay? So if, and I think it's an if and only if, so let's put it, f is conservative. Okay, so we'll put a big star there. F is conservative if and only if the curl of f is equal to the 0 vector. Okay, so that's the check you do. The first check you'll do if when you're doing one of these potential function problems and you have 3 variables instead of 2. If that's the case, you can't do this process where you take partials and see if they're equal. Okay, that won't work with 3 variables. You're going to have to do this curl f thing and show it's equal to 0. Okay, so let's look at one of those, in particular number 59. And they're giving us a vector field is sine z, sine x, sine y. Okay. Right, so the curl of this thing is, let me do our determinant here, partial x, partial y, partial z, and then m and p. So don't think of these as functions or anything like that. It's an operation on n. So it's just kind of reminding you, okay, I'm taking the partial with respect to x of n, and then subtracting the partial with respect to y of m. That sort of idea. Okay, so let's get in there and take a closer look. So first, cover up the column and row, and then it's the partial derivative with respect to y of p. Okay, so in that case, the partial derivative with respect to y of sine y is just cosine y minus the partial derivative with respect to z of n. Right? So n is this guy. With respect to z, the derivative of sine x is just 0. Okay, then minus, and cover up the second column and the first row. And then you're doing partial derivative with respect to x of p. So the partial with respect to x of sine y is 0. Minus the partial with respect to z of m. Partial of this with respect to z is cosine z. And then plus, finally, cover up the last column, first row, partial of x with respect, partial of n with respect to x. That would be cosine x minus the partial of m with respect to y. So the partial of that with respect to y is just 0. I lost my j, and this should be k. Sorry. All right. All right. So my final vector is cosine y, cosine z, and then cosine x. And that thing is not equal to 0 everywhere. Okay, it's not equal to the 0 vector everywhere. Sure, there's going to be points where it is equal to 0, but it's not equivalent to 0. Okay, so it's not the 0 vector. That implies it's not going to be conservative. I don't know if that means it's not conservative everywhere, but in our case, we're just going to kind of toss it out and say it's not conservative. Okay. So I don't know if there's an idea of. I bet there is some local conservative property, but we don't study that stuff. So just for us, we'll say it's not conservative and throw it in the trash. Okay. All right. The other operation that we'll introduce but not use is the divergence operation. And later on, we'll have kind of a geometric significance of this stuff. But for right now, we look at it in a purely math kind of way, without geometry, without physics. So this operation is a dot product. So you're basically taking partials of components and adding them together. Okay, so for instance, number 63, the divergence of this vector field is what we're after. Okay, so how do I do this? The notation is gradient dotted with f, the gradient symbol dotted with f, but what you're doing is kind of going to take the partial of this and then add in the partial of this. Okay, so you want to think of it like this. Okay, and then you're thinking, and it's not really, this times this anymore. It's the partial derivative of this. Okay, so the partial derivative of x squared with respect to x is 2x. Then the partial derivative of 2y squared with respect to y is 4y. Okay. Okay, so that's that. Let's see if I have any nice examples. Okay, I think I'll cut the video here, and if I have an example of a three-dimensional one, I'll put that up next. Okay. Okay, thanks for watching.